Welcome back. Now you can check your answers to the last three examples. As you can see, this one came out a no because they did have the same power, however, they didn't meet the other condition and have the same variables. In this next example, they met both conditions, same variables, and those variables were each raised to the exact same power. In our third example, the variables did indeed match, however, the second condition was not met. The exponents on our variables were not the same. So if you don't feel like you fully understood that or you didn't get those three examples correct, you may want to go back and relook at your definitions and examples and try again. Otherwise, you can move forward to the next part of this video. So we've got some helpful tips. All right, so looking at this next example, we're trying to identify like terms from a list, and there's a helpful tip here to maybe color code or organize in a chart. So first we're going to color code our like terms. So we have to identify them, and I'm going to circle the ones in the same color to identify that they are like. So I'm going to start with blue. So I'm looking at my list, negative 3x cubed. So I have an x cubed right there, so I'm going to circle my x cubes. In blue, I have negative 3x cubed, 5y, 6z squared, nope, 4x cubed, 4x, 2y, 8z squared, negative 7y. So those are all my x cubes, the ones circled in the blue. Now I'm going to select a color yellow, and I'm going to go to the next term in the list, which is 5y. So I am looking for a term that has a y to the first power. Z squared doesn't match, x doesn't match. I do have a 2y, that matches, y to the first power. And negative 7y also matches y to the first power. So those are like terms, I've circled them in yellow. The next term in my list is 6z squared. So I'm looking at the z to the second power. That would be what I am looking for to turn into my green color code here. So I circled that with green. I look at my next term that's available, 4x, not a like term. 8z squared, that is a like term. Same variable, same power. And my final term that I have that hasn't been circled with any like terms yet is 4x, and it's the last term, so it doesn't have any others but itself. So we've matched up these like terms. What we're going to be learning next is how to combine these like. All right, so now we have color-coded our like terms, and what we're going to do is take the items from here that are color-coded and put them into columns below, so we can start talking about what these coefficients mean that are in front of these terms. And that'll lead us into combining like terms, which is another target we have today. So we're working on that next target, building the idea for combining like terms. So at the top of the chart, I put that we have an x cubed term, y terms, z squared terms, and x terms. That's how I'm naming the terms, by their variable and their powers. And then the next thing I'm going to do is categorize how many of each of these terms I have by looking at the coefficient. For example, I'll take the term 4x cubed. I read that term as a multiplication throughout this lesson, that it means 4 times x cubed. So if I break that down, remember a coefficient is the number being multiplied to your variable. So if I break that down, multiplication is a shortened form of repeated addition. So what this basically means is I have 4 x cubes being added together. 4 of them being added together. So I can write an expanded form for this as repeated addition. So the shortened form is 4x cubed. So how many x cubed terms do I have? Well, this one says I have take away 3. I have minus 3 of them. And then this one says I have 4 of them. So I'm just stating the amount of each that I have in the column above. So our x cubed term, we have take away 3 of them, and we also have 4 of them. So I'm just writing those coefficients in the columns. And the next I have the y terms. I have 5 y's, 2 y's, and take away 7 y's. So I'm going to write that in the column. I have 5 altogether, then 2 more, and then take away 7. In my z squared, I have 6 of them here and then 8 more of them. So I have 6z squared and 8z squared. And in my final column is the x term. I'll just indicate colors above those real quick so we can see where those numbers are coming from in our chart from above. And my x term, I have 4 x's. So that would be another way to organize your like terms, by putting them in columns with the variable and exponent as the column title, and then how many of each of those you have in your list. So if I wanted to know how to simplify this mess, I could combine my like terms. You can combine your like terms by simply putting the coefficients together to find out how many you have all together. So looking at this first column, it says take away 3 and 4. So if we do the math on that, and we have our list over here all drawn out the long way, and I take away 3 of those, like it suggests, 1, 2, 3 of those in my list, I end up with 1x cubed, which is simply x cubed. So that's how we would combine our like terms. We would simply do the math on the coefficients and then tack the variable on when we're done. In my next example, it states that I have 5 y's, then 2 more y's, and then I take away 7 y's. So if I have my 5 y's being added together, I'm not going to put the plus signs in just to shorten things up. Just remember there are plus signs in between. And then I tack on 2 more. Here are my 5 that I started with. I had 2 more, and then I took off 7. 1, 2, 3, 4, 5, 6, 7. I end up with 0 y's left if I combine those like terms. So it's 5y plus 2 more y's, take away 7 y's, you end up with 0 y's in your problem. And remember, this means 0 times y, so you end up with no y term at all in your problem when you're done. In this next problem, it says I have z squareds. So I have 6 of them. We're adding them, remember. Z squared plus z squared plus z squared plus z squared. Da 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 da. I have 6 of them. And then I'm going to have to put on 8 more. And altogether, that means I have 14 z squareds when we're done combining them to make one term, make the problem a little simpler. And finally, you have your x term. There are 4, it's 4x. There's none to add or combine to that, so our answer is simply can't be simplified further than 4x. So the reason you might want to color code a list or put the list in a chart would be to help you simplify a long list of terms that is being added and subtracted from one another, and we call that combining like terms. So if I want to simplify this, if I have plus signs in between all of these terms, I'll throw them in for you, and minus signs are already there. Then what we can do is combine like terms, and what we would end up with is x cubed, taken from the first column. The y's canceled and went away. You could put in plus 0y if you wanted to see it, but ultimately that you would want to kind of put on your algebra big boy pants and simplify that to just nothing, to 0, and drop it. We'll get some practice in doing that a little later. And then plus 14z squared, because that's what our z's added up to, z squares added up to. And finally plus 4x. So this has been simplified from this version, and again, if you would really want to drop that term because it can be simplified to 0, and if you add 0 to any list of numbers, you'll get that list of numbers back. So it actually has no bearing on the problem anymore now that we've zeroed it out. So x cubed plus 14z squared plus 4x is your final simplified answer if you were asked to combine these terms and simplify the expression. You've created an equivalent expression for the big, long, ugly one up top. It isn't down into just a numerical answer because we have variables we don't know values for, but is definitely simpler than what we started with. Okay, we talked earlier, and this is just a reminder, that if you have a variable on its own, there's an assumed 1 in front for the identity property multiplication. It doesn't change it. 1 times y is y. 1 times any number is that number back. And that if there's no exponent written, there's an assumed 1 up on that exponent. So just keep that in mind when we start combining like terms. You don't want to be filling in zeros there because it's going to lead you into the wrong answer. So please make sure you're watching out for that common error of throwing zeros in front of variables or as their exponents. Okay, in our first example, we're asked to combine like terms. That means we're going to make this expression simpler if we can by adding the terms that have the same variables raised to the same powers. So one thing I recommended is that you color code. That's x to the first power, and that's 5. I'm going to circle the sign in front of my term along with the term itself. It's going to be important that we do that to recognize that we're adding 5x to the already x that we started with. So I'm going to be circling both the sign and the term when I color code. And over here I've made the chart. There's only one term in this particular algebraic expression. So I have here the 1. Remember, there's a 1 in front of the x, and the 5. So those are the coefficients. I have 1x plus 5 more x's. If you want to see that the long way, it would be 1x, that's the first one, and then 5 more, 3, 4, 5 more, for a total of 6 x's. Okay, 6 x's altogether being added. So you don't want to have to write this out all the time. So the shortcut is to recognize that you add the coefficients together, and that becomes your new coefficient with the variable, and you've made it simpler. X plus 5x is the equivalent of 6x. You don't need to write this down. I just want to walk you through why they're equivalent, why these two expressions are equal. If you take a 1 and plug it in for x in this expression, and you plug the same in here because it's x again, if you evaluate this expression for x equals 1, you get 1 plus 5 times 1, and 1 plus 5 times 1 is 6. If you take that same value for x and you plug it into your new expression that you created when you simplified by combining like terms, you get 6 times 1. 6 times 1 is also 6. Because we plugged the same number into both expressions and out popped the same simplified answer, then those two expressions are called equivalent expressions. So when you're combining like terms and you're done, you can pick a number to plug into both expressions to check to see if you did it right. If you don't get the same value, then you've made an error somewhere in your calculations. Our next example is 45a minus 37b. So to color code, I'm going to circle 45a in green. I'm going to check this one. It doesn't have an a, so they're not like terms. I'm now going to circle minus 37b because it's its own term in yellow. So I've color coded. I have two terms that are different. And so I cannot combine them if they are unlike terms, not like terms. So I'm actually done with this problem. There's no more simplifying I can do unless I find out what a and b are. So I leave this expression alone. Our final example is 7x squared plus 5x plus x squared plus negative 2. Go ahead and color code your like terms or put it in a chart and then turn the video back on to see how you did. Okay, you should have gotten that 7x squared and x squared were like terms, and that 5x and minus 2x were like terms. If you didn't get that, then you may want to fix your paper right now, and then I want you to combine the like terms on your own, turn the video back on to see how you did. Okay, looking at the color coding with the circling, you should have said 7 plus 1 is 8x squared, and that would be your x squared term, simplified, and 5 take away 2 is 3x. That would be your x term simplified. And so your final answer is 8x squared plus 3x. If you did the chart, you just simply add the two numbers in the chart for 8 on the first x squared, 8x squared, and then 5 take away 2 is 3 for 3x. So if you got that right, fabulous. If you did not, you may want to go back and re-look at the video with how to identify like terms and combine them. We just finished earlier. Now you need to go to video 3.